Still talking just about some programming stuff. Today we'll talk about loops and functions. All right. So we left off on Monday with conditions, and you had like if and else statements and things like that. And those are all great. We also have the if-else, which is useful. It's like a shortcut for assigning things if something is true, or assigning a different value if it's false. Okay. And so rather than having if x equal to 5, then n is yes, or else n is no, you can combine that, reduce that into if else x equal to 5, yes or no, and then assign that result to n. Okay? So you're combining the if else into this assignment. So the result of the if else is this yes and this no. Okay. All right. So we have for loops. Okay. This is probably our simplest and most common type of loop in R. You give it a vector, any kind of vector, and it iterates through those elements in the vector, and it evaluates the block of code for each element in that vector. Okay. And so, most commonly, the vector we give it will be like a vector of integers, like 1:10. All right, we'll just give it that, and it will it'll run through that vector. Okay, and so when we run this, it's going to do x squared. All right, so first it starts off with x equal to 1. It runs 1 squared, it says 1, then it goes to the next one. It goes, oh, x is now 2, 2 squared is 4, and so on and so forth, and we get this, right? 1 through 10 squared. Okay. Obviously, this could have just been written in vector notation without a loop at all, and that probably would be more efficient that way, but this is just for the sake of illustration here. Okay. Yes?
The step, is that to show that each element in the vector is different through the spaces that we use? Or?
No, so this is just cat. This is just cat output. This is not actually results that we can do anything with. It's just output to the screen, right? So cat just outputs things to the screen. So your question was?
The step with the quotation marks, what would happen if there was something else there instead of the 2 quotation marks?
Oh, like a comma?
Yeah.
Nothing. It would just put a comma there.
Oh, I see.
Okay, it just is that, right? Or I could have, and then so here, whatever you want. The default separator is a space. So this would have also worked, okay? I think this just squishes them all together. So we can just do that, right? Okay. Okay, on the next slide, it can go through any vector. So here I've created a list. So here, maybe it's easier to see this way. Okay, so here I've created a list. List is, if we ask what is L, it's this 1, 2, 3, A, B, C, D, E, F, G, and true, false. Okay, and so if I have the loop run through the same thing, basically for y and L, cat the length of y, what is this going to output? It'll output 372, right? So it goes through the first thing, and it says, oh, the length of that is 3. It goes through the next thing, oh, the length of that is 7. It goes through the last one, oh, what's the length? 2. Okay, so it's just running through the elements in L, which is this list, and it goes and it's printing out the length of that. Yeah.
What is the second line of the concatenation of true and false do?
What do you?
Oh, that's just the. Never mind. That's part of the list. Just kidding. Sorry.
Yeah. Okay. Okay, is that all right?
Perfect.
Yes.
How does it know that y is supposed to be an element in L?
Because we told it that. We said for y in L. So the for loop goes through a vector, and you say for, and then you just give it a placeholder. You say for the thing in vector, okay? So for number, you know, often it's for I as like a placeholder for a number in the vector 1 through 10, okay? That's probably your most common form of a for loop, you know, for x in 1 through 100 or something like that. And then it'll know, oh, x is 1, then x will be 2, then x will be 3, okay? But you can give it, the vector can be anything, okay? So if there's an internal data set called data sets, and you can look up state names, all right? It'll list off all 50 states. But if we just want the first 5, it'll be the strings Alabama, Alaska, Arizona, Arkansas, and California, okay? And then my loop can be for the state in state names 1 through 5, right? So it's going to say for these 5 things, each one, we're going to call it state, but I could have put whatever thing I want to call it. I could have said for x in state names, okay? And then what we're going to do is we're going to print out what we're going to cat the state, and then we're going to say has, and then we're going to look at how many letters that has, number of characters, and it'll say it has that many letters in it. So what will this put out? It'll say Alabama has 7 letters in it, and Alaska has 6, or something like that, okay? And this is our output here. Are these examples okay? Okay, so we're used to giving loops, these for loops, you know, 1 through 10 or whatever, but it'll accept any vector really. Okay. Okay. When we store the results of a vector, okay, it's almost always better to have the thing that we're going to store the results in. It's good to have that thing defined, and then just reassign the value to it. Okay, so here I've created a results vector, which is missing value 10 times. Okay, and then when I go through my loop, I'm going to say take the results, subset it to position x, okay, and then assign it the value x squared. Okay, so it's going to say, oh, the first time, take the thing in position 1, we're going to give it 1 squared. Then it goes through, take the thing in position 2, and give it 2 squared. Okay, so no big deal. All right, these are the results. And so the results itself, this is not concatenated output, it's an actual object called results now, and it's the numbers 1 through 10 squared. This is not an ideal way to go, all right? Here we're creating an empty vector, and then we're saying what we want to do is we're going to take the current vector and combine it with our new result. Right? And so effectively, each time you run this, you are copying the currently existing results vector, sticking something onto it, and then copying it over into the new results vector. Okay? Which, you know, with 10 iterations, it's going to make 0 difference. But with a million iterations, you'll feel the difference in computational time. Okay? Because this requires a lot more work, right? And then this one also bad in that you know, here we started off results is 0, and then we're going to say, okay, change the thing in position 1, then change the thing in position 2. Every time we do that, it requires that the results vector is resized. Okay, it says, oh, we've got to resize it to now accommodate 9 items. Now we have to resize it to accommodate 10 items and things like that. And that is not as bad as this, but it's still pretty bad. Okay. Yeah.
Is there a reason why you use NA to?
Yeah, you could have repeated 0 100 times or something. Generally, though, when you want to start off with where you're going to be storing values, you don't want to put in values that you might confuse with actual values, right? So you're like gonna do something. So maybe say like I want to do 10,000 things, and then for whatever reason when you're running your loop, maybe it only gets through 5,000. Okay, if you have 5,000 zeros after that, and then you start calculating the mean and the variance and all of that, you might mistakenly think that you've got some zeros. Okay, or you might not think that, but you might not notice that you've got 5,000 zeros still stored in your results vector. Okay, so if you put in NAs, either the computer will say, oh, you still have some missing values, or they're just not going to be factored into your calculations. So that's why it's better that way. But in terms of like the computer thinking part, no, it doesn't really make a difference. Okay. Yeah. Again, you know, if when you run something, you know, 10 iterations, it can be super poorly optimized in 10 iterations. You can do anything terrible for 10 iterations and it's not too bad, right? But then if it's poorly optimized and you want to do 1,000,000 of these things, then it's better to have it optimized, right? So okay, we have other things. We have while loops. Okay, and this it's going to keep repeating whatever's in the loop until this condition, the while condition, is false. Okay. This is very good if you're not sure how many iterations it takes. In this dumb example that I'm using, it's obvious that it's going to take 10 iterations for it to kick out, right? So in the thing I've got I, as long as I is less than or equal to 10, we're going to keep running this thing. And then inside the thing, I increment I to be I plus 1. Okay, so it's obviously that I is going to go to 2, then 3, then 4, and kick out when I is 11. Okay? But there are other times where, you know, later on we'll do some numerical methods where like you want to try to find the root. Okay, you want to find where the function is equal to 0. Okay, and because of the way computer math works, you're never going to get it. The result of the function will almost never be exactly 0. But you might get very close to 0, and there might be a point where you're like, okay, if it gets to be 10 to the minus 5 or smaller, that is good enough for me to say it's 0. Okay, and so probably in your calculations, you're going to have some kind of epsilon value that shows, you know, what's the difference between the thing and the thing that we're targeting. And you can say keep running the loop as long as your epsilon is greater than 10 to the minus 5. Okay, and that way you don't have to say do it for 100 iterations or 200 iterations, because you don't know exactly how many iterations it'll take. You're just going to say keep running it until your epsilon is less than 10 to the minus 5. Okay, or whatever convergence criterion you use. So that's when while loops are useful. A repeat is similar to a while, but it's a little different. Okay, repeat, you just put something inside curly braces, it'll keep running the repeat loop. Okay, but somewhere in there you should have the special word break. Okay, and this basically tells the thing keep repeating it until you run break. All right, and so generally you would have the break tied to an if statement, and in this case, if this thing runs true, then it's going to execute the break. So when I is greater than 10, then it will break. And so in this case, you know, it keeps squaring the values of I, and then it iterates I from 1 to 2 to 3, and then it goes, you know, I is 7. Is I greater than 10? Nope. We're going to keep running the loop. Okay. Finally, when I gets to 11, it's going to say, is I greater than 10? Ah, yes, it is. Okay, and then it executes the break. The break tells it stop the loop. All right, take, you know, break out of the loop, or just stop this looping. Okay, and then so that's a repeat loop. Okay, we have special keywords. We have break and we have next. Okay, break ends the current innermost loop, so you can have loops inside loops. All right. And if you're going to have a loop inside a loop, then break will stop the innermost loop, and then it'll continue on with the outer loop or whatever, okay? And then next just ends the current iteration. Okay? So in this case, we've got for I in 1 through 10, if I is divisible by 2, okay, so I mod 2 is 0, then break. Okay, and what that does is it's going to run, it goes 1, okay, so when I is 1, it looks at this is false, so it doesn't execute this. Then it goes cat, we're going to cat the I, and it prints out 1. And then it goes I is now 2, is 2 mod 2 0? Yes. So it executes break, and then it stops. And so the results of this is just 1. Okay. If I changed the word break to next, then this is what happens. Okay. It starts off with 1. 1 mod 2 is not true, so it does not execute this, and so it executes this, cat 1. So it prints out the 1. And then I is now 2, okay? And it runs this, it goes, oh, is 2 this? This part is true, so then it executes next. Okay, so as soon as it executes next, it goes back to the top of the loop and goes to the next iteration. It doesn't execute anything down here. Okay, so it skips over the 2, then it goes to the 3. And then 3, it prints it out. Then it goes to the 4, and so on. So here it's skipping every time you get an even number. Okay, so that's break and that's next, and those you can use, you know, whatever loops you want. Okay. You know, as far as the for loops go, a lot of times, you know, we're used to saying, you know, for I in 1 through 20 or whatever, things like that. We can do sequence or sequence along, sequence length. These are almost all the same thing, okay? But they're just kind of like shorthands for each other, however we think about it. Okay, so here is L is this list, right? If I look structure L, it's this. And so what is length of L? 3, right? Okay. So I could say, you know, 1 to 3. I could say 1 to length of L. And that will also be 1, 2, 3. Sequence along L basically looks at the length of L and creates a sequence from 1 to whatever that is. Okay, these are all the same thing. Okay, and we can do sequence length. Sequence length of 3 is also 1, 2, 3. Okay, so these are all kind of the same way of doing the same thing, right? So what would happen if I do sequence along letters? 1 to 26, okay, and that's all it is. Okay, so these functions exist, all right. I think I kind of probably default to just doing 1 : length of L, but you might see this also in other people's code and things like that. They're all there. Okay. So anyway, when you're working with loops and all of that, a lot of times it's better to do a vectorized solution. So if, you know, we could write the for loop to get 1 through 10, but I could have also just 1 through 10 squared, right? And then this would have done exactly what we wanted it to do, right? What if I wanted 1 through 10 squared and then 1 through 10 cubed and 1 through 10 to the 4th? Is that possible? Can I do that? So would this work? 1 through 10 2 through 4? What would happen here? It would go element by element, right? It would do 1 squared, 2 cubed, 3 to the 4th, 4 squared, 5 cubed, 6 to the 4th, and that's not what we wanted. Well, effectively what we want, I think, is, and I'm not sure if this will work, I think we want 2 through 4 on one axis, 1 through 10 on the other axis, and can I just do this? What is the... I don't remember what it's called. What's the power operator? Is there a power function? Create a power link. Power 2, 3? No. Okay, well, effectively, I want an outer 2 through 4, and then 1 through 10. Yeah, so, okay, so I think we would have to first create the matrix this way, and then we would run it. Yes, question or comment?
You can use function equal quotation mark and then the square sign. In outer function. Capital function. F-U-N.
Oh yeah, function equal, and then I do quote like this. Yes, that is what I wanted. I was trying to figure out the thing. Yes, and then so this is what we want. We want 2 through 4, and then so this is where the outer thing. You got to put it in quotes. Thank you. Okay, and then so yeah, you're like although it goes although this has it backwards from what I want. I want 1 through 10, 2 through 4 this way. Okay, and this is probably what I had in mind. Okay. Okay. All right, now we can talk about functions here. And so functions, you create them and you say name. You name the function, and then you say I'm going to make a function, and you give it the argument 1 and 2 and things like that. Then you give it the quote expressions to run, and then finally the function ends with a returned value or object. Okay. And so the way functions work is that they are objects like anything else. Okay. And if you only have one line, you can leave off the curly braces. Okay. Otherwise, it's probably a good idea to include the curly braces. And then and if you leave off the return, it will return the last thing that was evaluated. Okay. So in this case, I have defined a function like this. Okay. But to be more complete, I could write function of x, and I could write curly brace, and then say return x times x. Okay. These are effectively the same thing. Okay. And then I can say, what is f of 4? And it will do 4 times 4, and it will do 16, right? And I can say, f times of negative 4, and it will give 16 or something like that, right? If a function is a list, and a function is an object, so we can throw it into something like a list, right? And then so if I just throw it into a list, it'll be this. And if I ask what's the structure of this list, it'll say it's a list of 1, and the thing in that list is a function. Okay. If we ask R, what is that? The type of the function, right? What's type of f? It'll say it is a closure. Okay, so closure is just the way R calls these things that are functions. Okay, and you can pass functions as arguments into other functions and things like that. Okay, is that all right? Okay.
What do you mean by list of f?
It's just if I say list A is equal to 1 through 3, it just creates a list, right? I could just say list A is the function f, and then now it's in there.
Okay, so
You just a list is the trains, right? The train boxes. You can throw a function into one of the train boxes, okay, and there's no problem. Okay, so this this threw off the students last quarter, all right? So functions themselves can return other functions because functions are objects, right? And so when you ask the function to return something, the thing it returns could be a function, okay? And so, so here, f2 is a function of x. The thing it returns is a function of y, okay? And so I could say, you know, f2 of 5, this is now, the argument that f2 takes is a function, is x, okay? And so what it returns is a new function, all right? And then so this function is effectively an add 5 function, okay? And so add 5 is now a new function, and I could say we're going to give it 3, and it's going to return 8. Okay. I don't have to say take the results of f2 5 and call it add 5. I can just say, oh, the result of this thing itself, f2 5, this is a function itself, and I could say give it 3, and it will produce 8. Okay. Or you know, if I could, I can call it a new thing called make power. All right, and this could be a function of x, and what it returns, the thing it returns will be a function of y, that takes y and raises it to the x power. Okay, so make power is a function, all right, and then if I say make power 2, this would effectively be a squaring function. Okay, so I can call this the square function. Well, I don't know, squaring, just, okay, squaring will be make power 2, and then I can do squaring 7, and it will return 49, okay? And we can create a new function called cubing, and I would do make power 3, and then I can say cubing 4, and this will give back 64. So the result of a function could be another function itself. Right, and I don't have to explicitly name these things. I could just say make power 2, and then that itself is a function. Give that function the argument 8, and it will work. Okay, is that okay? So there is this kind of this functional power that that R has, and that you can. Functions can return other functions, okay? Because functions are just objects. So the thing that, so functions produce something to return. Generally, we're accustomed to having a function return a value, okay? But we could also say the function should return a list object. The function should return a function object, and that's fine. So we have explicit and implicit return values. Okay, the explicit case is that you specifically use this thing called return. So you write it inside the function, and it is going to return whatever is inside this thing. If you don't explicitly write return, it'll return the value from the last statement. That's what we have. So these two things are equivalent, but one uses explicitly the return. Okay, you can have it return multiple values. All right, x squared, x cubed. You run that, and you get this, 248. No problem. You can have it return a list. Okay, and this is, I think, a lot of the commands in R return the result of functions as lists. Like if you run linear model LM on something, the results of that is a list, but then they put it into class LM or something like that. And so, but basically that's just a list with some attributes attached to it. You run, t-test and things like that. The results of these things are generally lists. Okay, and so you can store all of these results that you want to keep track of in the list. And then, you know, if you have it like this and your function accepts things in kind of vectorized form, you can get all of these results in vectorized form as well. No problem. Okay. When we define a function, we're implicitly defining names for the arguments. Okay. And so, you know, when you say function of x, y, and z, your arguments, they're named. Names are x, y, and z, and this is also the default order that we're expecting the functions to be in. Okay, and so when you say give me a function of 1, 2, and 3, it matches them up and says x is 1, 2 is y, and z is 3. Okay, that's what it does. If you use the argument names, you can explicitly use them, and then you don't have to give them in the order that the function expects them. So it's expecting them in the order x, y, and z, but you can say, this time I'm going to give you z first, and then I'm going to give you x, and then I'm going to give you y. And it says, fine, I'll do that, and it will match them up accordingly. Okay. And then if you just give it 1, then it will assume the other ones come in the order that they're expecting. So right, if you just say y is 2, then the first one it will assume to match to x, and the next one to match to 3. Okay, so you know, if you use pnorm or whatever, they kind of have these default things, and so you know, this is why I often look up the help functions, right? So if you look up the help on pnorm, okay, it's expecting the values to come in q, then the mean, and then the standard deviation, and all of these other things there. And if you leave them off, it will take the default values. Okay, and so on. And if you give it an argument that is not part of the function, it will complain. It'll give you an error and say this is not an argument that we use. Yeah.
What if the number of argument is less than what the number of
the arguments in the function? So if you give it fewer arguments than what the function, so if you do that, then the function will stop and say, I don't have, you didn't give me a value. Okay. And one thing to handle that is you give it default values for the arguments. Okay, and that way it won't complain that it doesn't have enough arguments. So here I'll show you. Over here, so I'm defining this function. Okay, this is like a dumb function, right? So f is the function of x, y, and z, and if I say, okay, I'm going to give it 2, it's going to say argument y is missing, okay, and it doesn't have a default, so I give it 2 and 6, and it says z is missing, okay, so I say 2, 6, 9, and then it will run, okay. If you want to avoid that, then you give it some default values. So here we're saying, if you don't get anything for x, use 1. If you don't get anything for y, use 1. If you don't get anything for z, use 1, okay. Otherwise, obviously, use the given arguments. So here, if we don't give it any arguments, it'll use 1, 1, 1 for its things. Here, if I give it 2, it's going to match it up to the first argument and say, okay, x is 2, and it uses the defaults for the others. Okay, and then that way you can also say z is 3, and it will use the defaults for the other ones. Is that right? So for the arguments, you can give it defaults, and it also kind of implicitly defines the order in which the arguments should be provided. We have scope, and this is kind of a big deal. All right. If R is looking for a value and it doesn't find it in the current scope, it's going to search for it in the next higher scope. Okay. And so when you run a function, it kind of creates its own little bubble or its own little like sandbox, and it's expecting to find all of the values inside that bubble. Okay, so you give it, the way you give the function values is through the arguments. Okay, those go into the bubble, and it's expecting to have everything in there. If it doesn't find it in there, it's going to say, okay, I don't see what I'm looking for. I'm going to go to outside of my bubble and I'm going to search for this thing. Ah, I found it. And then it uses that. Okay? So here we're saying f is a function of x. Okay? And all we're doing is we're going to say x plus y. All right? And that doesn't matter. R doesn't care until we say, all right, run f of 3. When we say f of 3, it's going to take the x, it's going to plug in 3 for x, and it's going to say, okay, what I need to give back is 3 plus y. It's looking inside the bubble, and it's doing 3 plus y. I don't see a y anywhere. Okay, I'm going to look outside of my bubble, and it goes to the global scope, and it says, ah, y is equal to 1, and so now I can do 3 plus 1, and it returns back 4. Okay. Here, we're doing almost the same thing, except inside the bubble, we're defining y is to be 2. Okay? And so when I run g of 3 as this new function, it says, okay, I'm going to take 3 as my argument, plug that in for x. I need to return 3 plus y. Okay, well, I'm looking inside my bubble. Oh, 2 is right here. I'm going to do 3 plus 2, and I'm going to return 5. Okay? This y is equal to 2, or assignment of 2 to y, has nothing, does not interact with the y out here. Okay? So what happens inside the bubble just happens inside the bubble, and then as soon as the function or that scope finishes, poof, it's gone. Okay? So it's written here. So variables defined within a scope only exist in that scope and only for that duration of the scope. Okay? So if you have something outside of the scope, like we had the y is 2 inside the scope or inside the function, and we have a y equal to 1 outside, that's fine. Those are separate. They have nothing to do with each other, and they don't interact. Okay? The only way you get things in and out of the bubble is through the arguments of the function. That's the only way you get outside world stuff into the function. And then the only way you get stuff from inside the bubble back to the outside world is through the results, okay, or the returned object. Okay? So if you're keeping track of a whole bunch of stuff and you want to keep track of those and store those, you got to get those back into the outside world through the return. Okay, so you need to put them into a list in the return in order to keep track of it. Otherwise, as soon as the function finishes, those things are destroyed. Okay, so for example, if you execute, and this is a terrible idea, if you execute the code rm list equals ls, which is normally what we do to delete everything in our workspace, inside a function, you would only delete the objects that have been defined inside the function. Okay, and it wouldn't touch anything in the outside world. We have the super assignment, which I asked you guys to look up in your homework, and that is the one that searches a higher scope, okay, and eventually the global environment if it doesn't find it in that higher scope. Okay, so here I have maybe we'll look at this here. I'm going to clear everything out. Okay, so I'm going to define x, y, and z are all equal to 1. Okay, and here I'm going to create this function. All right, and if we look at the function, inside the function I'm assigning the value 2 to y, and inside that function I'm creating a new function g. Okay, inside g I'm assigning the value 3 to z. And then it's going to ask to return x plus y plus z. Okay? And so when you run f, it's going to, and the result of f is that it should return the result of the g function. Okay? So then it's going to execute g. It's going to say, okay, what I need to return is x plus y plus z. Okay? I'm looking for x. I don't see x anywhere. I go to the next higher scope. I don't see x anywhere there. I go to the highest scope. I find 1. X is 1. I look for y. I don't see anything here. I go to the next higher scope. Ah, y is 2. I'm going to use 2 for y. Then it goes to z. I'm looking for z. That is right here in my own little bubble. And so it's going to use the values 1, 2, and 3. So finally, when I execute f, it's going to return 6. We look at the values of x, y, and z inside the global environment, and those are, and that's fine, okay? That's just the value 6. I mean, those are still untouched at 1, and the result of f is 6. Okay, so x, y, and z still remain 1. And then I can print out the values of x, y, and z, and we see they're all 1, 1, 1. Okay, over here I'm defining x, y, and z as 1, 1, and 1 again. And inside, this is almost exactly the same code, except I've just replaced the assignment with the super assignment. Okay, so right now they haven't been run, right? I have not executed any of this code. I've just defined them inside the function. And this code will only be run when I run the function f. Okay, when I run the function f, it's going to run this code, and what it's looking for is to return the function result of g. And when it runs g, okay, it's going to look for x, and again, it doesn't find it until it reaches the top. Okay, then it's going to look for y, and it's going to keep searching, and when it runs this code here, it's going to assign the y up in this scope here. And then the z, it's giving the super assignment of 3 to z. Okay, it's going to look for z in the higher scope, and then it's going to look for it in the highest scope, and it's going to change the value here. So when I run the code, you'll notice that the values of x, y, and z will change because those super assignment commands have been run. Okay, so x, y, and z are now 1, 2, and 3, and it returns the value 6. Okay, so the super assignment no longer plays inside the sandbox, but it goes to the higher scope. Is that right?
What's the point of doing that?
So there are times when you want to do it this way. It is dangerous because you might start overwriting things in the global environment that you didn't intend to, you don't want to mess with. Okay, but there are times where you want to keep track of a bunch of things, and for whatever reason, you can't get it into the returned value. Okay, and in that case, it makes sense to go into the global environment and mess with things there. Okay, but again, you have to think of a function as the only way it interacts with the outside world is it gets input through the arguments, and then it outputs the results. Okay, and so you want a function that does something. Okay, if you want to, the only way you can get it is through the results, and if you want to affect something else inside your function and you can't think of the way to do it through the results or the return value, you're going to use super assignment. Okay, but again, you got to be careful because it could be dangerous. Right? Yeah, question.
Why are these examples returning functions like you showed earlier in class? Like, why isn't the function giving a function as an output since you're using f and y?
Because the function, the return, the thing that we're asking f to return is g, which is not the function g, but it's g parentheses, which is execute g. Okay, and when we execute g, it's going to return a value. So what it's asking to return is we're not asking it to return the function. We're asking it to return the result of executing the function. Okay, so right, if you ask mean, it's going to try to run the command, the function mean. Where if you leave off mean, if you leave off the parentheses, it's not going to execute that function. It's going to actually tell you, oh, you want me to define this function for you, right? And this uses use method mean, right? Which doesn't help us, but so when you tell it, if you ask what is f, f is this function that we've defined. If you want to execute f, you've got to give it the parentheses, and then it'll run it. Okay, and so here I'm going to just show you one more thing. All right, so so here I've got x, y, and z. Y I'm defining to be 2 inside the bubble, right? This is regular old assignment. This y is being defined inside the bubble. Here I've got y super assignment 4. Okay, this 4 assigns, it doesn't even bother with the y inside my current scope. It goes to the y outside of this. Okay, And so this 4 will overwrite this y, whereas this will still remain 2, okay? And then here I've got z superassignment 3, so it's going to look for it in here, it doesn't find it, and then it goes to the parent one here, okay? And so here, when I return x, y, and z, what is it going to give me? Oh, the answer's already there. Okay, it's going to give us 6, right? So, because it's not going to use the 4 that's in the global, it's going to use the 3, which gets put into the global, but it's going to use the 2, which is inside the next bubble, which is defined inside that bubble there. Okay, and so we see that that's there. What would happen if I define a z here to be 10? So we're going to have x, y, z, and then I'm going to run this. Okay, after I run f, what will it return? And what will the global values be? Will this z be changed to 3, or will the z be remain 1? Will it return? Yeah. Okay. Well, all right. Let's see what happens. All right. Huh?
Will it return the z? Oh, just kidding.
Okay. So here, it gets evaluated to 6, right? So what's going on here? So it takes this z superassignment, it searches the next higher scope, it finds the z here, and so overwrites this z here. Okay? Because there's a z in this scope, it's not going to try to reach the global scope. So the global scope z remains 1 because it found it here. Whereas the previous version, this wasn't there, so it kept searching for the z in the higher scope. So it searched the higher scope, it didn't find it, so it went to the higher scope and it overwrote the z in the global scope. Okay? So, and then here the y, it doesn't touch this y, it goes immediately to the highest y, and it overwrites that. Okay? And then so if I have it this way, so here I got rid of the z in the higher scope. This z assigned 3 will search until it finds the z and it overwrites it, and then so now this gets overwritten to be 143. Is that all right? All of the scoping stuff? It's a little confusing, I get it. I understand that. It's just it searches the higher scope until it finds the thing that it's looking for, and then it will write it there. Okay. All right, and then so anyway, we use functions to encapsulate a small piece of reusable code that we can use again and again and again. That's when it makes sense to run a function, and that's how it goes. Okay, we have infix operators that well, you can look at this. Don't worry about it too much. All right, we'll see you guys